Okay, and so let's take a look at your activity 3, that is your physical exam of urine. And so with this, and so under your physical exam, you have your uh, urine clarity, and so that is, of course, your urine clarity, your urine color, and your urine specific gravity. And so they are actually included in your uh, physical exam, and of course they are included in your report. Okay, and so your urine odor, and so still it's part of the physical exam, but then it is not reported. Okay, and so it is not reported, but then you accordingly urine odor is somewhat valuable, and so because there are distinct odors, and so that will what you call this identify a disease, an underlying disease. Okay, and so with this, let's take a look at your physical exam urine. And so let's take a look at your changes in your unpreserved urine. Okay, and so of course, and so your changes in your unpreserved urine and so will take place, of course, right after. But then, and so metabolic changes is actually speed up, and so 2 hours after the urine is left at room temperature without any interventions. Okay, and so let's take a look at your changes in your unpreserved urine. And so you have your decreased and your increased analytes. Okay, and so with this, and so let's take a look at your increased analytes. Okay, and so you have your pH, and so your pH, and so it will cause an increase. Your pH actually is increased. Okay, and so your pH is increased, and so because of bacterial breakdown of urea to ammonia, and so that is by your urease producing bacteria. And so other than that, and so an increase in pH may be caused by loss of carbon dioxide, and so by the loss of carbon dioxide, probably if you expose it, and so it will, of course, the carbon dioxide will escape, and so giving you a urine pH of somewhat alkaline. Okay, and so your microorganisms, your bacteria, and so they will increase. And so this is because, of course, you have your bacterial multiplication in this one. Also, and so your odor, and so will increase. And so normally your odor, a normal urine odor is aromatic. And so, but then when there is an increase in odor, and so probably, and so you have your urea to ammonia again, and so this is caused by your breakdown of your urea to ammonia, and so by your urease producing bacteria again, and so your normal odor of urine is aromatic, and so but then upon prolonged standing, and so it will give you ammoniacal odor, and so it will give you ammoniacal odor, and so for this one, and so of course this one is caused by your microorganisms, bacteria again. Okay, and then your nitrite, and so your nitrite, and so that will there is an increase in the nitrite, and so due to the multiplication of your nitrate reducing bacteria, and so your nitrate is reduced into nitrite. And so if you are asked, and so about your nitrate, then of course, so when you're asked about the nitrate present in the urine, and so in a prolonged stunting, and so there will be a decrease in the nitrate present. Okay, and so usually this nitrate, and so the specimen for your nitrite, and so is tested using yan is tested using best evaluated using a first morning urine. Okay, and so you have as such, and then you have your modified, and so you're modified, and so you have your oxidation, the color, and so you have your color here, and so that is probably due to the oxidation or reduction of your metabolites. And so remember in the lecture that we talk about your urobilin, and so your urobilin, that is the oxidized form of urobilinogen, and that one will impart your urobilinogen, and so will impart a dark brown color, and so a dark yellow color on a urine that is left standing at room temperature without any interventions like preservatives added or refrigeration. Okay, and so your color, and so that is modified or darkened, and so due to the oxidation or the reduction of metabolites present in the urine. Okay, let's take a look at the decreased analytes. Okay, and so you have here decreased clarity, and so probably and so normal urine, and so has a somewhat clear. Okay, and so you have here the decrease in clarity is caused by, and so you have your bacterial growth and precipitation of your amorphous material. Okay, and so you have precipitation of your amorphous material, you have your amorphous phosphate and your amorphous urates. Okay, and then of course you have your bacterial multiplication with this one. Okay, and so also you have your glucose is decreased, and so uh your glucose is decreased, and so with this, and so that is caused by glycolysis and bacterial use, of course. And so when there is metabolism, and so that is glycolysis by the cells, uh by other cells present. Let's say you have RBCs, WBCs present in your urine, then of course they will also utilize the glucose present. Also, ayan, so your bacterial metabolism will contribute to the decrease in the glucose content of your urine. And so with this, your unpreserved urine is the most common cause of false negatives in your glucose testing. Again, and so unpreserved urine is the most common cause of false negative in glucose testing for your urine. Okay, and then of course you have your ketones, and so your ketones, and so they what they call this, they are also decreased, and so due to volatilization and volatilization and bacterial metabolism also. And then your conjugated bilirubin, and so or bilirubin, and so that is a photooxidation to your biliverdin. Okay, and so photooxidation to biliverdin. Okay, and so with that, or of course, exposure to light. And so with that, it also with this in this one, bilirubin in your urine, and so also applies. And so with the changes that will take place when you expose a serum sample, a blood sample into uh, light. And so when you expose it to light, probably, and so sunlight. Okay, and so urobilinogen also, ayan, so oxidation to urobilinogen, ayan, so will cause its decrease. And then you have your cast, and so your cells, and your RBCs, your WBCs with this, and so they will disintegrate. Ayan, so of course with this, ayan, so alkaline urine, and so let's say for example, you have an increase in bacteria, ayan, so you have your urease producing microorganisms present in your urine. Of course, with that, it will cause an increase in the urine pH, and of course, this alkaline urine will cause a the disintegration of your cast, your cells, like your RBCs and your WBCs present in your urine. Of course, and so when you're going to read that one, and so mawawala na po sila. And so you have there, and then you have your trichomonas, and so there is a loss of motility and probably, and so you have death of the trichomonas, of course. And so when you will read it, and so in case that there is trichomonas in the urine, and so you will not appreciate you will not appreciate it, and so you will not appreciate the motility, and probably, and so you can mistake it as you can read it mistakenly as WBC accordingly. Okay, and so you have as such. Okay, and so of course, and so you have your urine clarity. And so how do you do this? How do you check on your urine clarity? And so of course, you visually examine the sample in a clear container. And so while holding it in front of a light source. And so with this, of course, and so that is why, and so a translucent urine container accordingly is advisable to use. Okay, and so with this, you have your variations in your urine clarity. Again, and so your normal urine clarity is usually clear. And so your normal urine clarity is usually clear. And so especially if that is midstream clean catch. Okay, and so let's take a look at your variations in your urine clarity. And so of course, we do report clear, hazy, cloudy, turbid, and milky. And so, but then again, and so please follow when you will work as a medical technologist soon. And so uh, you follow the SOP set by your institution. And so with this, when you say clear, and so there is no visible particulate. There is no visible particulate, and that is transparent. When you say hazy, and so you have few particulates present, and newsprint is easily seen through the urine. Okay, and so usually, and so you do newsprint in this one. Okay, and so hazy, few particulates present, and newsprint is easily seen through the urine. And then you have cloudy, many particulates, and newsprint is blurred, and so through the urine. And then when you have a turbid sample, and so newsprint cannot be seen, and milky, and so that is may precipitate or be clotted accordingly. And so may precipitate or be that is clotted. Okay, and so that is for your urine clarity again. And so you have your clear, hazy, cloudy, turbid, and milky. And so please know this one by heart. Your changes accordingly can be observed after 2 hours of standing at a room temperature without any interventions, chemically or physically. And so that is why most laboratories, and so they require the urine sample to be submitted within 1 hour after collection. And so within 1 hour after collection. And so, and then of course, the remaining 1 hour will be utilized for testing. And then of course, and so 2 hours after standing, and so it will changes, and so can already be observed. Like of course you have there your increase in odor, clarity, and so and decrease in clarity, and so and decrease in glucose and the rest of the analytes to be tested in your urine sample. Okay, and so with this, and so we're going to take a look at your specific gravity. Okay, and so we're going to take a look at your specific gravity. And so what does your specific gravity mean? And so again, it is defined as the density of a solution compared with a density of similar volume of water at a similar temperature. Okay, and so at a similar temperature. Of course, this one, your specific gravity is utilized. And so it is utilized to measure the concentrating and diluting ability of the kidneys. Okay, and so of course, with its a function, and so to maintain equilibrium in the body. Okay, and so with such, and so your specific gravity, and so it is affected by both the number and size of particles in a solution. And so comparing it to your osmolarity, and so when you say osmolarity, and so it is only dependent on the number of particles only. Okay, and so with such, of course, and so with this one, and so your specific gravity, and so is an indicator of concentration of your dissolved materials in your urine. Okay, and so your first, of course, and so you have as such your specific gravity measurements. And so let's take a look first at your refractometer or your total solids meter. Okay, and so with this, of course, it is the one that is recommended by CLSI. And so it is recommended by CLSI. Okay, and so with this, of course, and so it is calibrated. Okay, and so in doing so, and so of course, you calibrate the refractometer using 1 or 2 drops of distilled water. Okay, and so the reading should be equal to 1.00. 1.000. Okay, and so with the one. Okay, and so 1 or 2 drops of distilled water with this one. Although, and so you can do calibration, and so you can do other calibrators, like you have your 5% sodium chloride. Again, and so you have your 5% sodium chloride at 1.022, and so you add or you subtract 0.001, and so you have it as 1.021 to 1.023 when you're using your sodium chloride. When you will use 9% sucrose, when you will use 9% sucrose, and so you do the what you call this, the reading should be 1.033 to 1.035. Okay, and so you can still, and so distilled water, triple distilled water, you use when you use the one, you have it at 1.000, and so you have as such. Okay, and so with that, when you already calibrate, please note that in the calibration for your refractometer or total solids meter, if you're using this one in the laboratory, it should be done daily. Ayan, so daily po ginagawa ang calibration nito. Okay, and so of course, after you did your calibration, ayan, so you rinse the surface of the prism and cover with water, then dry. Okay, and so you dry it, and then after that you put 1 or 2 drops of urine sample on the prism, and so make sure that the prism is covered with your sample, and so there should be no bubbles should be, and so as such. And then of course you close, after that you close the cover plate gently, and allow the sample to be drawn under the cover, and so by capillary action again, and so the sample must spread. Okay, and so it should spread all over the prism. And then, of course, you hold the instrument against a light source and read the specific gravity through the eyepiece. Okay, and so through the eyepiece. Okay, and so, of course, if you already have such, then you record it, and so you record it as your specific gravity. And so, okay, what is the principle employed in your refractometer or your total solids meter? And so that is, it measures your refractive index. And so by that, it does not directly measure specific gravity. Okay, and so it measures the refractive index, which is a comparison of the velocity of light in air with the velocity of light in a solution. Again, and so it measures the refractive index, which is a comparison of the velocity of light in air with the velocity of light in a solution. Okay, and so with this, the path of light is deviated when it enters a solution, and the degree of deviation or refraction is proportional to the density of a solution. Okay, and so that is for your total solids meter or your refractometer. And so it utilizes a refractive index. And so the degree of refraction is proportional to the density of the solution. Okay, and so this one accordingly is recommended over your hydrometer. And so, of course, the advantage, it uses a small amount of sample. And so, 1 or 2 drops of your sample, and so is needed for this one. But then, wait, and so you have actually a correction for your specific, for your refractometer. And so, you have here with this, of course, and so when using the refractometer, and so the temperature, and so can range from 15 degrees Celsius to 38 degrees Celsius, no? And so with this, you do not need to do corrections in temperature reading. And so while comparing it to your urinometer, that you need to do so. And so again, in your refractometer, and so you do not need to do corrections in the temperature of your sample. Okay, and so because it is calibrated between 15 degrees Celsius to 38 degrees Celsius. But then you have corrections. And so we talk about this one in the lecture. And so to have this one. And so what are your corrections here? Of course, and so you have here for every 1 gram of glucose, 1 gram per dl of glucose, and so for every 1 gram per dl of your glucose, you subtract 0.004 to your reading. And so you have as such. And then for every 1 gram per dl of your protein, you subtract 0.003 of you subtract 0.003 per 1 gram per dl of protein to your reading. Okay, and so as such. Okay. Ayan, so you have here. And so that is for your refractometer. And so moving on, let's take a look at your urinometer. And so your urinometer, and so it is your urinometer. And so, of course, with this, and so your urinometer is otherwise known as hydrometer. And so it's otherwise known as a hydrometer. And so accordingly, this one is not recommended by Clinical and Laboratory Standards Institute. And so with this, you have here, and so the major disadvantage, the major disadvantage for your urinometer is it requires a large volume. And so with this, and so it requires a large volume. And so for this one, it requires you to fill the cylinder of your urinometer set at 2/3 full. And so, according to Henry, and so you have 15 ml. And so 15 ml, but then other references, and so include 10 to 15 ml. Okay, and so you have as such. Okay, and so the urine should have a temperature of 20 degrees Celsius. If hindi po siya naka 20 degrees Celsius yung the temperature of the urine, you need to do corrections. And so let's take a look at that later. Okay, and so again, your urinometer is uh, not recommended, and so that is accordingly less accurate. Okay, and so you have this one. Okay, and so let's take a look, and so at this urinometer. And so for this, and so the corrections in temperature, and so if the urine is colder, and so if the urine is colder than 20 degrees Celsius or that is lower than 20 degrees Celsius, ayan, so you subtract 0.001 from the reading for every 3 degrees Celsius that the sample is below 20 degrees Celsius. And then, if the sample is warmer, ayan, so warmer than 20 degrees Celsius, then you add 0.001 from the reading for every 3 degrees Celsius that the sample is above 20 degrees Celsius. Okay? And so you have as such. Okay, and so for corrections using your glucose for glucose and protein, and so it will also follow with the corrections done in your refractometer. And so you subtract 0.004 for every 1 gram per dl of glucose, and you subtract 0.003 for every 1 gram per dl of protein. Okay, and so you have as such, of course, and so for the calibration, and so may use, you can do uh distilled water, and so calibrated at 1.000. And so when you use potassium sulfate solution, and so the reading should be at 1.014. And so but then most common you have your distilled water, since that is almost always available, and so at calibrated at 1.000 using your distilled water. Okay, and so how are you going to use your urinometer? And so urine, of course, you mix your urine thoroughly and allowed to come at room temperature. And then you fill the cylinder of the urinometer, and so 2/3 full with urine. And so again, and so that is usually 15 ml. And so with a slight motion, and so you spin the urinometer to prevent it from touching the sides of the urinometer. And then, of course, you read the bottom of the meniscus while looking at the hydrometer at eye level. And so with this, and so care must be taken. And so, of course, your urinometer manometer, the hydrometer must not touch the sides of your cylinder and must not also touch the bottom of the cylinder. And so it should be free floating. Okay, and so it should be free floating. Okay, and so again, you add your hydrometer in a spinning motion. Okay, and so you have as such. Again, and so you remove any foam, and so which may be present because the bubbles will interfere with the reading. Okay, and so as such. Next, your reagent strips. And so of course, with the use of your reagent strip. And so your reagent strip, and so it provides a simple, rapid means for performing medically significant chemical analysis. No, and so including an chemical analysis of urine, including your pH, your protein, your glucose, ketones, so blood, bilirubin, urine-specific gravity, urinobilinogen, specific gravity, nitrite, and leukocytes. And so with this, of course, there is a color-producing chemical reaction that will take place when the absorbent pads comes in contact with your urine. Okay, and so of course your reaction are interpreted by comparing the color produced on the pad with a chart supplied by the manufacturer. That is your comparator block, no? And so you have as such. Okay, and so let's take a look first at the care of your, at your reagent strip technique. And so you dip the reagent strip completely, and so but briefly, and so into your well-mixed specimen. And so remove excess urine from the strip by touching the edge of the strip to the container as the strip is withdrawn, and then blot the edge of the strip on a disposable absorbent pad, and wait the specified amount of time the reaction to occur. And then, of course, you compare the color reaction of the strips to the manufacturer's comparator block. And so in a good lighting, of course. Okay, and so care of your reagent strip, of course. Let's take a look. And so store with a desiccant in an opaque, tightly closed container. And so store below 30 degrees Celsius. Do not freeze, no? Do not expose to volatile fumes. Do not use past the expiration date, of course. And so and so still do not use past the expiration date, no? Do not use if the chemical pads become discolored. Yes, usually, and so when it expires, kasi, and so the reagent strip, the reagent pads, the chemical pads will also be discolored, okay? Remove strips, and so immediately prior to use. And close. So, close tightly the reagent bottle. Okay, and so the bottle with such because of course to prevent no oxidation of your of the chemicals present in your reagent pad. Okay, and for the quality control, and so you have your test open bottles of your reagent strips with known positive and negative control every 24 hours. And so every 24 hours, no? And so resolve control results that are out of range by further testing. Okay, and so test reagents used in backup tests with positive and negative controls. And so you have backup tests, like of course you do your chemical testing, like your heat and acetic acid, SSA, Benedict's test, and so if you have such, and then perform positive and negative controls on your reagents and newly opened bottles of your reagent strips. And so of course also new lot number, ayan, and record all your control results and reagent lot numbers. And so, of course, with that. And so, let's take a look at your principles employed. And so, in your reagent strips. And so, you have actually uh, 10. And so, for your 10 parameters. And so, let's take a look at your 10 parameters. No? And so, but then, you have actually 11 and 14. And so, for the 11th pad, you have it as the ascorbic acid. And so, but then let's take a look at the principles of your glucose. And so, your principle here is your double sequential enzyme. Okay, and so for your glucose, it utilizes your principal double sequential enzyme reaction. And so, double sequential enzyme reaction. And so, of course, you have your enzymes and so your glucose oxidase and your peroxidase. And of course, and so your chromogen employed is your potassium iodide, and so that will change from blue to green to brown. And so with that one. Okay, also your tetramethylbenzidine that is employed in your chemistry, and so that will change from yellow to green as such. Okay, and so glucose plus, of course, your what you call this oxygen, and so in the presence of peroxidase, and so will give you your gluconic acid and your H2O2. And so that is for your principle of your glucose. Your ketones. And so your ketones, the principle is you have your sodium nitroprusside reaction. And so, or otherwise known as your Legal's test. And so for your Legal's test, and so for your sodium nitroprusside reaction, and so in your ketones, you have your sodium nitroprusside or your sodium nitrofuranide and glycine. Okay, and so you have as such. Of course, you have your acetoacetic acid, and so plus your sodium nitroprusside, and so will give you a purple color. And so with this, and so it utilizes your sodium nitro. When you say sodium nitroprusside only, and so it will detect your acetoacetic acid only. And so if there is an addition of glycine, it will detect your acetoacetic acid and your acetone. Okay, and so the positive result for your ketone, for your sodium nitroprusside reaction test for your ketones, you have it as your purple. And so purple. Okay, and so purple color. Next, you have your specific gravity. And so your specific gravity, and so the principle is a change in acid dissociation constant. No? And so you have your pKa change of your polyelectrolyte. And so you have your reagent, I mean your uh, color indicator, you have it as your bromthymol blue. And so your bromthymol blue. Okay? And so you have as such. Of course, and so with this, of course, and so uh, the change in your polyelectrolytes, and so when there is an increase in electrolytes present, in ions present in your solution, and so there is a change, what they call this, in the dissociation constant. And so with this, there is an increase in the release of your hydrogen ions. And of course, with that, it will be translated into, it will cause a change in the color reaction. Okay, and so with this one. Okay. And so for this, you have your blue to green. And so for the one in your alkaline pH. And then in your acidic pH, you have it as yellow to green. Okay. And so you have, for a false increase, you have high concentrations of your protein. And so please note that uh, your specific gravity in your reagent strip is not affected by glucose, your protein, and the radiographic contrast media. But high concentrations of protein present will cause a false increase. Please note of the word high here. High concentration. Okay, and so false decrease, and so that is probably caused by highly alkaline urine at greater than pH 6.5. And so with this, you add 0.005 to the reading when pH is greater than 6.5. And so, of course, due to the interference of your bromthymol blue indicator for this. Okay, your pH. And so the principle employed is your double sequential enzyme. Sorry, double indicator system. And so double indicator system. And so the reagents present. And so you have your bromthymol blue and your methyl red. Okay, and so bromthymol blue and methyl red. And so with this, there is no known interferences, interfering substance. And so just the run over from adjacent pads. And of course, your old specimen, no? And so you have here, of course. And so when you have a pH of 4 to 6, and so you have red to orange to yellow. And then when you have a pH of 6 to 9, then you will have a green to blue color. Okay, and so alkaline, and so pH of 6 to 9, you have a green to blue color, and then a pH of 4 to 6, then you have a red to orange, red orange to yellow. Okay, okay, your proteins. And so your proteins, the principle employed for your proteins is your protein error of indicators, or your Sorensen's error of indicators. And so with this, and so you have your reagents, it utilizes your tetrabromophenol blue or your tetrachlorophenol tetrabromosulfonphthalein. Okay, and it utilizes an acid buffer, your citrate. And so you have here. And so, of course, your indicator, and so your indicator plus your protein, and so will give you a color change, no? And so a color change, and so a blue-green color will give you a positive protein. Okay, and then you have your blood. And so your blood, the principle employed is your pseudoperoxidase activity of hemoglobin. Okay, and so the reagents used, and so for your multi-sticks, you have it as your diisopropylbenzene, dihydroperoxide tetramethylbenzidine. For your chem strip, your dimethyl dihydro peroxyhexane tetramethylbenzidine. Ayan, so you have as such. And so, but note that you have it as benzidine. Okay, and so you have there with this again, and so that is your pseudoperoxidase activity of your hemoglobin as such. Okay, and so your peroxide, hydrogen peroxide, and so plus your chromogen, and so H2O2, and so pseudoperoxidase, and so H2O2 plus your chromogen, and so will give you oxidized chromogen, a color of what they call this, a color of green to blue. Okay, and so a green to blue. Okay, and so with this, when you have a spotted blue, and so that is for your intact RBCs. When you have a uniform blue color, and so that is for your hemoglobin and myoglobin. Okay, and so your pseudoperoxidase activity of hemoglobin for your blood. Okay, bilirubin. And so your bilirubin, and so it utilizes your diazo reaction. And so it utilizes your diazo reaction. You have here, it utilizes your 2,4-dichloroaniline diazonium salt. And so, and for your chem strip, and so you have your 2,6-dichlorobenzene diazonium salt. No? And so you have your, for this, and so the reaction, you have your bilirubin glucuronide or bilirubin dichloroanide, and so plus your diazonium salt, and so will give you an azo di. Okay, and so we'll give you an azo di with such. Okay, next your urobilinogen, and so your urobilinogen, and so that is the principle employed is your Ehrlich's reaction, and so you have here your reagents used. You have your para-dimethylaminobenzyaldehyde or your PDAB or your Ehrlich's reagent, and your for your chem strip you have your 4-methoxybenzene diazonium tetrafluoroborate. And so it's such. And so in this, and so in your multi-sticks, and so you have your urobilinogen plus your PDAB, and so will give you a red color. And then your urobilinogen plus your diazonium salt, and so will give you red azo dye for such. Okay, and so red as the positive result. And then your nitrite. Your nitrite, it utilizes your Grice reaction. And so utilizes your para-arsenic acid and benzoquinone. Okay, and so tetrahydrobenzoquinone. And then you have your chem strip, your sulfanilamide plus your hydroxy tetrahydrobenzoquinoline. Okay, and so you have there. And so for that, the positive result for this one is a pink color. and so a pink color. Okay, so for your leukocyte, and so the principle employed is your hydrolysis of your acid ester, and so probably with such, okay? And so in your leukocyte esterase, okay? And so you have your reagents accordingly, your derivatized pyrrole amino acid ester, and so in diazonium salt in your multisticks, and your endoxyl carbonic acid ester diazonium salt in your chem strip. And so with this, and so your endoxycarbonic acid ester, and so you have here will produce you a purple azo dye for the positive result. Okay, and so you have here for your leukocyte. And then for your 11th pad, and so reagent pad, you have here your ascorbic acid accordingly. And so your ascorbic acid. With this, it causes false negative reactions on blood, bilirubin, leukocyte esterase, nitrite, and glucose. And so addition, and so for your addition, as what I've said earlier, you have an addition of your uh, addition to 14 reagent pads, you have your calcium. And so calcium is added, calcium pad, albumin pad, and your creatinine pad accordingly. And so that is for your 14 parameters, no? Ayan, so yeah. But then the 11th pad, that is your ascorbic acid. Okay? And so that is for your, of course, your activity number 3. Okay, and so you have here actually an illustration of your 10 parameter reagent pads, no? And so you have your leukocyte, your nitrite, your urobilinogen, your protein, your pH, your blood, your specific gravity. And so with this, for generally, and so you place you when you're using refrigerated sample, and so you place them under, you bring them at a room temperature, and so you bring them at a room temperature because actually your reagent pads, and so the reagents present, they are the reactions that will take place, and so they are somewhat temperature dependent, and so accordingly they are somewhat temperature dependent. Okay, and so you have here, but then for your specific gravity, and so this one, your specific gravity accordingly is not affected by temperature. And so you have here, but then for the general use of such, and so when you are using a refrigerated sample, you bring your sample at room temperature, and so at room temperature, because generally, and so the reactions that will take place in your reagent strip, in your reagent pads, and so are temperature dependent. Okay, and so of course that will be for your activity 3. Okay.